then we closed on the idea of geostrophy. So geostrophy, we want to understand better than just the equations. We actually want to have a pretty deep understanding of how it works. So we're going to go back and look at that in more detail and talk about how to think about it in different settings. Okay? All right, so we saw that little movie. Okay, so there we go. So here are the slides for geostrophy, and I have neatly put myself right on top of the figure that I wanted to talk about. What we can talk about. Okay, if there is low pressure next to high pressure, and the sense of rotation is the sense of the northern hemisphere, like this, what happens? What do those equations tell us? There are two ways to read the pressure field. And we could either read it as a curl kind of thing in relation to this, or we can just see like there's part of the gradient here and part of the gradient here. So which way does that force push? Let's draw X and Y on here. Okay, so what's dp dy? Which direction does that go? That's the y direction. And there's a low pressure, high pressure, and a low pressure. If I'm down here, which way does dp dy point? It points toward high pressure, this way. Not minus dp dy, which we're going to get to in a second. So minus 1 over rho dp dy points this way. What about here? Minus dp dy points this way. What about here? And like that. So it's so minus the pressure is pointing inward toward the center of a low and outward from a high. Pressure, okay, and what about in this direction? dp dx. Which way is that pointing? From low to high. So dp dx is pointing out this way. Oops, other way. This way. So that's rather confusing. This is where you're starting to see there's something funny going on because u and v have different signs because there's a cross product hiding in there. It's really f cross the horizontal velocity equals the gradient of the pressure. So there's a minus sign in one equation and not in the other. But let's just write it as it is here. So which way does FUG point? If F is positive, because we're in the northern hemisphere frame, for the dp dy part, which way does it go here? Careful. It's U, not V. To the right. dp dy is this way, minus dp dy is this way, which is a positive number. So FUG should be positive. Let's do a different color for the velocities so we don't get confused. What about here? Same argument, opposite direction. What about here? Same argument, this direction, this direction. Okay. What about the other equation? So VG is which direction? Maybe I should have said this. Oceanographers always like to put alphabetical order for the components of the velocity and the components of the coordinate system. So X, Y, Z goes to U, V, W. So U is the X component of the velocity, V is the Y component, Z is the W, W is the Z component. Sorry, I didn't say that. It's sort of standard in fluid dynamics, but we should be explicit about it right now. Okay, because that's why we drew these as X components. Okay, over here, what about this one? So this is what is this? A positive dp dx or a negative dp dx? So negative dp dx. So that means that v is what? Positive or negative? Negative. Positive, negative, positive. Okay. So, lots of weird things happening. Which way does the pressure gradient force push when there's high pressure? Out. The velocity, the geostrophic velocity that is in balance with that pressure gradient force is radial, not outward. The flow goes around the high pressure, and the flow goes around the low pressure in different directions. Yeah, I know. Very weird. That's one weird thing about geostrophic flow. Another really weird thing about geostrophic flow, which might be the weirdest thing still, which is going to be one of the most complicated parts of what we have to think about this class, is what happened to the DDT? We dropped it, right? Because the Rossby number was small, which meant that F cross U was bigger than... But this is no longer an equation that predicts velocities anymore. It's a diagnostic relation. So we've lost... Knowing that the velocity in this moment is this tells us nothing about the future velocity, or at least not from this equation. It just says whenever I've got a pressure field, I've got a velocity. That's extremely weird because we just lowered the time derivative order. We've also, remember how we talked about when you make an approximation and throw out an equation, you might lose a boundary condition? We've just lost an initial condition here on velocity. We don't even have an initial velocity. We don't need one anymore. The velocity is instantaneously determined from the pressure field, which should be extremely surprising. So this is a really different equation than this one. And for the first 50 years of dynamical atmosphere and ocean science, they didn't know what to do with that. So it took them a very long time to figure out how to build a governing set of equations that made sense if you wanted this to be the leading order velocity field, because you kind of always needed this guy to evolve the equations. So we're going to continue talking about that a lot. That's going to be a big part of that's what quasi-geostrophy is all about. That's what planetary geostrophy is all about. It's about making this approximation for at least the leading order velocity, but still being able to evolve the velocity somehow. Just not with that equation. Okay? All right, so we've got an outward force in this case and an inward force in this case, and we've got flow around. That's what those equations say. So how do we think about that? What's the force balance look like? Maybe looking at the top equation and throwing out the first two terms. What two terms are balanced here? Coriolis and pressure gradient. So F cross U balances minus 1 over rho nabla P. Okay, so we just said nabla P, I need a third color chart, blue. Okay, force balance. Nabla P is pointing in to this, or minus nabla P, pointing out here. Which way does the Coriolis force have to point then? It's got to oppose it, or if we put them on the same side of the equation, they would oppose. It should be in the same direction in this, the way I've written it here with a minus sign. So basically, we need a Coriolis force that's opposing this pressure gradient force to keep it spiraling happily around. So how do I think about that from F cross U? How do I get a Coriolis force that's either inward or outward? What's the direction of F cross U? If F is in the vertical, how do I use my right-hand rule?
Y direction.
So I take the F direction and then I cross it into the direction of the velocity, right? So this way, this way, this way, this way. Does everybody know that right-hand rule? Sorry, this is a weird, it's that you take your fingers, you start at the first one, and then you curl them over to the second one. The direction of your thumb is the direction of the cross product. So I'm trying to illustrate that here with the F being this way, and then I curl in the direction of velocity. If the velocity is going around and around, indeed, the Coriolis force is in and out. Does that make sense to everybody? So F cross U is either in or out, and because we already went through and got the signs right, it will be the correct one. So if this flow is going this way, so F cross U is out, same direction as that, out, same direction as that, out, same direction as that, out, same direction as that. In this case, going around the other direction, it's F cross U is in, F cross U is in, F cross U is in, F cross U is in. Okay? So the reason it's spiraling is because the Coriolis force is perpendicular to the direction of motion, and we want that to be in the same direction as the pressure gradient force. That's how it works. So which way do we go? Around a low, clockwise or counterclockwise? Counterclockwise in the northern hemisphere, which is a direction called cyclonic, and this is called anticyclonic. So cyclonic is always for a low pressure, anticyclonic is always for a high pressure. In the northern hemisphere, cyclonic is counterclockwise, anticyclonic is clockwise. In the southern hemisphere, cyclonic is clockwise, anticyclonic is counterclockwise. Why is that? What? Because F changes sign. When you're looking from the bottom, it's going the other way. Okay? Everybody, so we'll keep going through that, but I want to show you some movies and stuff to illustrate this. Okay, so these are the bullet points which Valis nicely puts out, and you should go back and look at these again and really make sure you understand each of these in great detail. So geostrophic flow is parallel to the lines of constant pressure. Why is it parallel?
It's perpendicular to the pressure.
Exactly. It has to be perpendicular to the pressure gradient in order for the Coriolis force to be in the same direction as the pressure gradient. So the flow has to be along the isobars, along the lines of parallel pressure, in order to have the gradient directions work out. And if F equals greater than 0, the flow is anti-clockwise around a region of low pressure, that's cyclonic, and clockwise around a region of high pressure, anticyclonic. Okay? The Coriolis force is constant, and if the Coriolis force is constant and the density does not vary in the horizontal, the geostrophic flow is horizontally non-divergent. So he doesn't even mean the Coriolis force is constant. He means if F is constant, which is a bit frustrating. If I take the divergence of these two equations, what happens? If I take ddx of this and ddy of that, what happens to the other side? If the density is constant. I get minus ddx ddy of p and plus ddx dy of p. So this geostrophic velocity does not diverge, which we're going to come back to over and over again. That's this little piece. The scaling for the kinematic pressure is no longer good for this. We'll come back to that later. Okay. So, in order to illustrate this, I want to show you a lab experiment where they basically fill a tank full of stuff and then pull the plug in the middle. And you're going to see what happens at different rates of rotation in that system. Okay? So if I pull the plug in the middle, is it a low pressure anomaly or a high pressure anomaly? Low, right? Because the stuff is going to go down and inward. So it'll be low pressure here compared to here. So it'll be what, a cyclone or an anticyclone? Cyclone. So if they're rotating it in the sense of the rate rotation of the northern hemisphere, this will be counterclockwise in this setting. So it should spiral inward like that. And this is what the lab setup looks like. There's a little tank. We're looking from above. It's spinning. Okay, so here is a non-rotating case, or gently rotating case. So see the dot? It's just a floating blob. He's putting it on the outside. It's going, there's a little deflection of the Coriolis force. The deflection is toward the right of the motion, which is another way of thinking of which way the Coriolis force pushes you. But it's, in a sense, as to spiral counterclockwise.
It's not rotating, right?
It's rotating gently. So what do you think happens if we rotate faster?
The deviation is much bigger.
Right. So in this sense, you can think of the Coriolis as just a mild deviation from going down the plug hole. Now, in a faster rotating, you see that it goes around many more times before it goes in. So the dominant motion is actually not down the drain. The dominant motion is perpendicular to the pressure field. So in this sense, the geostrophic velocity is much bigger than the down the plug hole velocity. At lower rotations, the down the plug hole velocity was bigger. The geostrophic velocity was a weak perturbation. Everybody on board with this? Okay. Oh, I don't have any volume. You guys see this part? This is fun. People often claim that this makes the toilet flush one way or the other.
Oh, for Pete's sake, Bart, use the plunger. Bart, water will only go the other way in the southern hemisphere. What the hell is the southern hemisphere? Haven't you ever looked at your globe? See, the southern hemisphere is made up of everything below the equator. This line. So down there in, say, Argentina or Rand McNally, all their water runs backwards? Uh-huh. In fact, in Rand McNally, they wear hats on their feet and hamburgers eat people. Cool.
This is only about 3 minutes long, but it's worth it.
Hello, southern hemisphere. Which way does the water go in your toilet?
Just a minute, I'll check.
Nuts. Please to repeat again, and I will translating for the El Presidente.
Which way does the water turn in your toilet?
Dice que el curso está cambiando.
¡Ay, caramba! Los insurgentes ya van a capturar la capital. Necesito huir. ¡Ay!
I can't get a straight answer out of this crazy hemisphere.
Eine Minute. Ach, das Wagenphone ist eine Nuisance-Phone. Buenas noches, mein Führer. Ja.
Bart, you can't actually call these places. Don't you know how expensive international calls are? Hello, operator. I'd like to make a collect call to Australia.
This is the international operator. Will you accept a collect call from...
Yes. This is Dr. Bart Simpson of the International Drainage Commission. It's an emergency. If it's an emergency, then... We understand some drains in your area have been malfunctioning, sucking in people and whatnot. Really, Kaz? That's awful. Indeed. We need you to check your sinks and toilets and tell us which way the water is going. And please, stand clear. The fixtures, they're all draining clockwise, sir. Oh, she was right, stupid Lisa Science Queen.
All right, that's it. But actually, in the toilets, it's interesting. If you figure out the Rossby number of the toilets, it's actually really hard to get them to flush the right direction. So you should not feel if you stir the water like he's doing before you flush it, it definitely will go the other way. And there's a whole other set of videos about people on the equator taking tourists from one side to the other and showing them pulling a plug hole. And so for this experiment, well, I'm going to go back to it. Hold on. For the experiment that we were just looking at, where is it? For this experiment, you can see there's all these rocks and stuff out there. That's actually to make it have no net motion as it comes in. It needs to flow purely radially through this direction before going out the plug hole. If you don't do that, you can stir the tank in advance and get it to go either way. Or you have to let the tank sit very, very gently for like many, many hours before you do the experiment so that all the residual motion has died out. Because the way you filled the tank, if you put the hose in one direction or the other direction, that residual vorticity will actually last for hours. So it's quite, to do this right is actually much harder than you'd think. But anyway, Bart's example is funny. Okay, so dimensional analysis of this. Oh, so this is where I was hoping that this thing was not going to go. Let's see if we can slide it out of the way briefly. Oh, I can. If the Coriolis parameter is not constant, when we take, what happens when we take d dx of this direction? If x is in the east-west direction. If f varies, like on the beta plane, what happens? Nothing. But if f does depend on y, and this is the north-south direction, we would get an extra term, which is this term. So this is v times the y derivative of x. So you do have a small but very highly predictable divergence in that case on the beta plane. So we're going to talk a lot about this when we think about how the beta plane works. So the motion does converge, but in a very precise balance between the convergence and the gradients in the rate of rotation. Okay? Because the divergence is small, remember we did last time, we did, oops, I'm going to use this terrible chalk if I don't have to. Del u equals 0. So when we scaled this equation, we had du hat dx hat times u over L plus dw hat dz hat. And this one is w scale over h equals 0. I'm sorry, I'm just going to drop the y one because to make it so. In order for this term to balance this term, what does it say about u and L and w and h? They have to be the same size. So u over L is the same size as w over h. Or you could say that means that w is the size of u times h over L, or however you want. So it's if the aspect ratio is wide, then w is smaller than u. That was what we talked about last time. This is how we got the hydrostatic balance. But, I do need the y term. d hat, dy hat, plus. What if these are dominantly geostrophic? Which means that the horizontal divergence of these is close to 0. Then what happens here? Is this a good scaling? No. Because aside from the size of u and the size of L, if there's a near cancellation between these two terms all the time, this thing is going to be 0 at the leading order. This size, it'll be smaller. And so that's the way that the scaling works out. It goes like the aspect ratio squared, which is what we did before, times the Rossby number squared. So when the Rossby number is small, w gets even smaller. How do we know it's Rossby number? Where did that come from? Go back through all these videos. Where's the Rossby number in this, scaling this top equation? So if these two terms are size u squared over L and this term is f over u, if I divide the whole equation by u squared over L, I get a 1 over Rossby number right here. So the size of this term compared to this term is 1 over Rossby. So when we drop this, it means small Rossby number, which means this term is bigger than this one. But in this divergence-less conversation, this is the part that still diverges, this is the part that doesn't. So instead of spinning around the plug hole and not diverging, if you go in the plug hole fast, it means these terms are rivaling this term. So the size of the convergence is order of these terms versus this term, order Rossby. So instead of this scaling, we get a Rossby number on it. So when Rossby number is small, it makes the divergence small, which then leads to this. Everybody on board with that? Sort of. We'll keep coming back to this. Okay. Grab myself and pull myself back in here so that we sort of have the right video. Okay. All right. Okay, so now let's talk about some of the... What happens if nothing interesting happens? That's sort of oops. This thing is not working very well. What if we take those equations and only look at the geostrophic velocity? So put this and this together inside a gradient, and suppose the density is constant, or at least that I can bring the density inside and write it inside of a gradient like this. No friction, small Rossby number. This is what I get. Everybody see that? We could take the curl of this equation, which for those of you who've seen a lot of fluids means we're forming a vorticity equation. So curl of this whole thing. What's the curl of this side? 0, because everything's inside of a gradient. So the first step in this Taylor-Proudman effect is just to note that those two terms, if the density is constant, I can write it as a gradient. And then when I take the curl of that gradient, I get 0 on this side. So now the Coriolis, it's like the cheese stands alone. The Coriolis force stands alone when we take the curl. So only the Coriolis force is participating in the vorticity budget. This is hard to think about. Some of you might have that to think about it. So instead, we use a triple product rule. We go through, and we find this. This is the same as this, or we can drop the minus sign because it's not important. 2 omega dot gradient of v equals 0. What does that mean? Which way is 2 omega pointing? It's in the rotation axis direction. So in this case, pure vertical on the f-plane. So if the gradient of the velocity in that direction is 0, what does that mean about the flow here? Which way is the gradient in the vertical, or the gradient out of the board in this case?
0.
It's 0. So what does that mean about the flow? So if I'm going around, now we have to imagine that this is like a fluid that's moving around like this. What does it mean that the velocity gradient is 0 in this direction? It's the same value. So whether I'm looking over here, or over here, or over here, they all have to be moving together. There's no differential in motion between the part closest to the board and the part furthest away. Or in the lab tank, he was putting that little dot at the surface, but you could have put a dot in the middle and it would have gone just as fast, because there should be no shear in a strong geostrophic motion if the density is constant and the friction is negligible. That's the Taylor-Proudman theorem. So when we think about what's going on, here's another one. So this is our rotating stirred problem. Remember the non-rotating one had turbulent kind of cloud-shaped things of tracer. But what happens here when he puts the die in and it's a strongly rotating case? How is the motion spreading? Is it tipping over motion? It's not. It's like a curtain of dye. So it goes down, but then it moves like this, where it's moving at the same speed at the top and the bottom because of the Taylor-Proudman effect. There is no shear in the vertical direction when you have constant density fluid and negligible friction. And so now when he zooms in, you can see there's a little tiny bit of shear in an oscillation, but it's not persistent. So what does that tell you about the equation of motion? Let's go back. That top equation. So we said, okay, let's neglect friction. These guys, when we put them in, they go into a gradient, so they cancel out. So what's that little oscillation? What is it telling us about this versus this? Well, which one of those terms is going to lead to an oscillation? That's the first thing. The one with time in it, probably.
And omega.
And the one with omega, put those together, maybe you could have a more interesting solution than this equation. You could have a ddt plus this, so you could oscillate together. That's the inertial oscillation. It's not as big as the part dropping the time, which is the geostrophic velocity, because of the Rossby number in that tank. So you can get different balances, and in fact this one might be much bigger than that one, but in this case this is much smaller, but the little small amount of this mostly just balances this guy in the inertial oscillations. Okay?
The time period can only come out of omega, right? If only those two terms are there.
The time, this omega?
Yeah.
If only these two terms are there, then you need both of them to make an oscillation. So it's actually, so for an oscillation you need two time derivatives, not one, right? If you have one, you could have an exponential growth or an exponential decay. And the way this works is because of the cross product, so the U equation has a V here, and then the V equation has a U here. So when you put them together, you get two time derivatives for the U equation or two time derivatives for the V equation, and that's the oscillation. That's the homework problem, actually. So if you haven't already done that one, that's a huge hint as to how to get started. Okay? Does that make sense to everybody? So Taylor-Proudman theorem, in the limit of just totally neglecting the time derivative, tells us the motion is just like this. But if we keep a little bit of time derivative, we could have a little wobble that would have a little shear and inertial oscillation. Or maybe it doesn't have shear. It could also be a wobble on the horizontal. But that rigidity of columnar motion. So this is what I said, the Taylor towers or the Proudman pillars. But normally they're called Taylor columns because people are less focused on the poetry. Anyway, the Taylor columns move around. And so there's this great, I'm told, not true story. But anyway, apparently Taylor was doing lab experiments like this, and he put a little platform at the bottom, and he noticed that the die would never go onto the platform. It would just go around. Because to go onto the platform, you'd actually have to converge, right? Because you'd have to squeeze whatever that Taylor column was. And it seems to be very resistant to that. So he was totally mystified by this, and we'll talk more about this. So he then put a goldfish in the tank and put food on top of the little pillar to see if the goldfish would swim up. And the goldfish did not swim up onto the pillar. It would get food anywhere else, but it would not go there because there was so much resistance to getting it on top of the pillar. Apparently this is not at all true. He didn't do it. He just thought about doing it, but he didn't think it was fair to the goldfish to put them in a rapidly rotating tank in the first place, so it never happened, but it's a good story. Okay. All right, so here are some examples looking from the side of the tank. We have that curved surface. What's that? Curved surface is there. Why? Pressure gradient has to balance the centrifugal force that we've totally forgotten about because we just absorbed it into the geopotential But if you look closely at the surface of those tanks, yeah, it will be curved when you're spinning because of that. But it doesn't do anything else to the motion except for make that curved surface. So here are some Taylor columns that I've drawn on top. Why are they in this direction? Is it because of the direction of gravity, or the direction of the net centrifugal plus gravity, or the direction of the axis of rotation? It's the axis of rotation. So the fact that the G force is not down, Taylor columns don't care about that in this case. Okay, so the motion isn't sheared in the direction of the axis of rotation. What about on a planet? So now the axis of rotation is always this way. And gravity and centrifugal. So which way did Taylor columns point there? They're not actually in the vertical. They have a horizontal component to them. So in the tilted F plane, the Taylor columns are not vertical. They're aligned with the rotation axis. In the F plane, or the beta plane, we approximate them as being vertical because in this direction, you're constantly actually banging into stratification, which would change some of the assumptions in the underlying Proudman theorem. Remember, we had to bring the density inside, assuming it was constant. So if you do this, if you tried to do that calculation in something that's density stratified in the direction of the net of gravity and centrifugal force, you would actually find that the Taylor-Proudman theorem doesn't hold in that direction, but it still holds pretty well in the local vertical direction, because in that direction, you can still pull everybody inside of the gradient, and you can take a two-dimensional curl rather than a three-dimensional curl. The curl just in the direction of the vertical, okay? On gas giants, where there's not a whole lot of stratification, down at the equator, it may be actually that the Taylor columns penetrate all the way from one hemisphere to the other hemisphere, and that the columnar motion might be believable. And you might not have believed that looking in the old pictures of Jupiter, but when you look down from the new pictures at the top of Jupiter, you say, oh my gosh, there are all kinds of vortical motions that are aligned with the rotation axis. And maybe those stripes were actually vortices that were sliced by the equator. So it's not totally clear whether they're connected or not. We don't know. But this is an interesting topic of extraterrestrial GFD that people are thinking about now. And here's some more of those the vortices at the edges from Juno that are cool to look at. Okay, so now we have hydrostatic balance and we have the geostrophic balance. So what's the hydrostatic balance tells us what? What's the force balance implied? Gravity, or net of gravity and Coriolis, centrifugal. The balance is what?
Vertical pressure.
Vertical pressure gradient. Okay, what's geostrophy tell us? Horizontal pressure gradient is balanced by what? Coriolis force. So we can put those two together and get something that's called the thermal wind balance. So here's our geostrophic relation. And sorry, Valis has once again switched from whether he's calling it pressure or pressure over density. But anyway, this is the geostrophic balance. This is the hydrostatic balance. So the buoyancy is the same as the gravity piece, being the pressure in the z derivative. I could take ddz of this equation and ddz of this equation, and then I'd have a d phi dz, and I'd have a d phi dz. On this side, I'd have an f du dz, because f doesn't change in the vertical, but u certainly might. This side, f dv dz, which is these equations. So is this motion sheared in the direction of the rotation axis? Yes. In fact, that's what's predicted here. The thermal wind is the deviation away from the Taylor-Proudman effect. The Taylor-Proudman effect says rotation stiffens things in that rotation axis direction. The thermal wind relation says horizontal buoyancy gradients allow shear. Okay, so they're sort of in opposition. When you rotate the tank, the motion tends to get more stiff in the vertical. When you put stratification in the tank, and especially horizontal, so gradients in stratification, you then allow vertical shear again. So sometimes people talk about the stratification as lubricating in the vertical direction, which is kind of an odd way to think about it, but that's it makes it less stiff, and rotation tends to stiffen it. So there's a competition in that sense between the stratification effects and the rotation effects. So in our rotating stratified turbulence problem, we're always going to be interested in whether one or the other is dominating or whether one and the other are in balance. Okay? And this applies when the aspect ratio is small because we have the hydrostatic balance, and the Rossby number is small so that we have the geostrophic balance. Geostrophic plus hydrostatic equals thermal wind. These are the two conditions to have it happen. Okay, so on that note, if we're thinking about scales of motion and we have an idea of stiffening due to rotation and loosening or whatever, allowing shear due to stratification, how could I describe the vertical scale of motion versus the horizontal scale of motion, including stratification and rotation? And just a dimensional analysis or thinking. So I have H, which is my vertical scale of motion. I have L, which is my horizontal scale. What is our parameter to describe the rate of rotation? Rossby number, or just F, if we're thinking of a dimensional one. What's our parameter for amount of stratification? We talked a little about stable stratification and unstable stratification. We need to talk more about it. Does anybody remember?
Frequency?
The buoyancy frequency. So N. So if I want to write, for a motion of a given horizontal scale, if I want to write a vertical scale that gets taller when F gets bigger and gets shorter when N gets bigger, the units of this are 1 over time. The units of this are 1 over time. This is a length scale. This is a length scale. So what can I do with these guys to write that? So if I want it to get taller when F gets bigger. Let's see if I did it right. I could write it like that. Or the more traditional way to write it is like this. This is a special length scale called the Rossby deformation radius. This is the length scale at which the stiffening effect of F is balanced by the lubricating effect of stratification. This is a central thing that we're going to keep seeing this. This is going to pop up over and over again. It's sort of just dimensional analysis, a little bit of thing about thermal wind and Taylor's, but it's really a little more generic than that. And what this means is, in normal turbulence, no length scale is special, right? You have the injection scale that makes the energy, and the dissipation scale that takes care of it much smaller, but in between, every length scale is the same. This is a special length scale. So if we go to big enough scales that rotation and stratification are experienced, this scale is going to qualitatively change the kind of turbulence nearby. Okay? So this is a road marker on our set of things to think about. Okay? All right. For those of you who took my oceanography class, I have brought back the pillows and bricks. So this is about buoyant. So to think about the thermal wind relationship, something that's buoyant or less dense, I make stacks of pillows, and something that is more dense, I make stacks of bricks. And then you're supposed to think about how these affect the pressure gradient. So how does the pressure increase as you go down in a stack of pillows? Slowly, because pillows are light. When the pressure increases fast in bricks as you go down because they're dense, right? So when Vallis writes this elaborate diagram, if you put the stack of pillows next to it, it's much easier to figure out what's going on. So if I have a high stack of pillows, slightly higher than a stack of bricks, I might have a pressure gradient that's going, sorry, if I got that backwards. Yes, no, a high pressure here, low pressure there. So a pressure gradient that's this way, a pressure gradient force that's that way. When I go down here, I've got high pressure on this side, low pressure on this side. So my pressure gradient goes the other way. In that case, the buoyancy gradient, see the buoyancy gradient that's in green, why is it always pointing this way? Why is the buoyancy gradient pointing this way at all heights? Yeah, the pillows are buoyant. Pillows will float, bricks will sink. These are more buoyant than those. So buoyancy is pointing this way. And then if we think about the geostrophic force to balance this pressure gradient, it would be this way, the geostrophic velocity, and the geostrophic velocity to balance the pressure gradient this way is this way. So there is a shear in the geostrophic velocities because of the presence of the buoyancy gradient. That's what this equation tells you. So it's a long way to go graphically to get there. But essentially, the idea is if dense stuff is sitting next to light stuff, you're going to change the direction of your pressure gradients as you go up and down in the vertical, the horizontal pressure gradients. And that's what this little diagram is meant to illustrate. This happens in the gyres in the ocean, where where you have tall stacks of pillows, places where the water above the thermocline is thick, and short stacks of pillows where the water above the thermocline is shallow, and then different heights of stacks of bricks below, which is an oceanography class question. You can think about this in terms of these kind of things with, upwelling and downwelling features. This is a map of the pressure field in the oceans at nominally 5 meters of depth, but there's higher pressure here, lower pressure here. So if there's high pressure here, is it a cyclone or an anticyclone? An anticyclone, so it should go clockwise, which in fact is the direction of the North Pacific Gyre. It's also the direction of the North Atlantic Gyre, the Gulf Stream and the Curacao. If you go this way in the southern hemisphere, that's also the direction of the gyres. Going this way for the ACC is also the right way to go for the geostrophic pressures. And if I go deeper down, do you think the currents are the same if I go deep? Yes, maybe, no? They would be if it was Taylor-Proudman. How would they not be? Horizontal temperature gradients. So we might have horizontal gradients. If I go deeper, so this is now nominally at 1,533 meters depth, all of these currents are gone. The ACC is still there, but below the picnic line, below the density gradients, there's very relatively weak geostrophic motion, only strong in the ACC. So that means that in between that surface and below, there had to be horizontal density gradients in order to have the thermal wind cancel out whatever velocities there were at the top before you got to the bottom. So in the oceans, the thermal wind, outside of the ACC, the thermal wind is actually winning in its play against the Taylor-Proudman theorem, and the currents are pretty surface intensified. In the ACC, they actually go all the way to the bottom for complicated other reasons, but you can think of it as more like a Taylor-Proudman style flow. Okay? And so that's bits and pieces. Let's look at some movies, and then we'll be done. All right, so this is showing one density interface. So this is like a gyre. There's a wind blowing. This is one density level. It's colder up here and warmer down here. So this is showing just where this particular density class it appears. This is where it's at the surface and kind of the mid, and then it goes down below other things as you go down here. And up here it just doesn't exist. That density is too light for northward of that. And these lines are not exactly pressure lines. They're a little bit more general than the pressure lines. They're the Montgomery potential. But they're essentially the isobars. And the motion you can see is flowing kind of along those and then going around in a loop like this. And this is showing the thickness of this layer, the color. So if you think about it, this is actually a high pressure. It is here where the layer is thick, lower pressure here. So we're getting the flow in the direction we'd expect from both the geostrophic and thermal wind relation. If we go to a deeper level, it looks similar, except it's at a different density, so it's a little bit different. Go to a deeper layer still. Now we start to see the effects of the wind direction in the other direction on the top. And so you can see that there's cyclones and anticyclones kind of superimposed, having to do with the way that the pressure field varies in both the vertical and the horizontal. Does that make sense to everybody to some extent? So this is the usual one to keep in mind from Vallis. We'll come back to this one over and over again, but the other stuff is sort of bigger flavors. Next time, here we go. So we can go through the review of balances, which for those of you who took my oceanography class, you're bored of seeing these. But we can do the scaling of these equations, and then we can think about different dominant balances that might occur between different terms and what we call them. And so we've now covered most of these. We'll get the rest of them next time. Does that make sense? So next thing to try is to study how these equations work when we have hydrostatic and when we have geostrophic balance. Like, can we simplify those equations and study what ways to solve them? And it's going to turn out that we can, of course, otherwise we wouldn't be doing it. But we'll talk about the shallow water equations, and we'll talk about the quasi-geostrophic and the planetary geostrophic equations as being implementations of how to solve these equations in those limits. Make sense? Cool. And so Friday, I will also give you the homework key, and we'll start doing the peer review process. So we'll talk a little bit about that, which isn't so much except just to make brief comments for other people kind of, but really it's my method of guaranteeing that everyone is looking carefully both at the key and at any comments on their homework, and that everybody's getting a lot of comments on their homework, more than I have time to do in everyone's homework. So we're using a scalable solution to the homework problem, the homework grading problem. Okay, cool.